In the method of weighted residuals, if you make this particular choice of weighting function, it turns out that you can show that this is equivalent to minimizing the energy in the residual, in the error here. So pause the video and try this for yourself. As usual, directly skipping to the result is, as you know, a waste of your time, unfortunately. Let's first of all explicitly write down what this energy in the residual is, or the norm squared of our error. So it's a scalar product of R with respect to R. And we know that our residual takes the following form. It's L operating upon some ui bi of x minus v of x. So that's the form of the residual. So for the second factor, we can also then write that this is the following. So hopefully on the other side of the screen by now there's a huge uproar, because again this is the product of two series expansions, so we should really use a different summation index for the second series, otherwise we're going to end up into trouble. Okay, so this is what the residual looks like. So now what we should actually do to show that this is equivalent to solving the weighted residual method with a particular choice of weighting functions, what we should do is we should find the u values that actually minimize this thing. So the way we're going to do that is to take the derivative with respect to all possible values uk and put those equal to 0. So in case you were stuck, now could be a good time to pause the video again and try again. Let's expand the energy here. So abbreviating this as follows. So first we have the product of this sum with that sum. So that's going to be L summation over I ui bix times L summation over j on the other hand uj bj of x, right? Then for the second term, let's take this one with that one. So that's going to be, so v has a minus sign, so let's bring that minus sign outside. Summation over I ui bi of x and then v of x. Okay. For the third term, we have minus vx times that summation. Now in this case, we no longer have the product of two series expansions. It's just a single series expansion. So you will easily realize if you just expand out that series, it doesn't really matter whether the summation index here is called I or j or whatever. So we can just as well call this I. And we're also going to assume that our scalar product commutes so that we can switch the order, so that we can first start with the summation and then have v. And if we do that, we realize that this is exactly the same term as we already had before. So in this space, which I cleverly left open here, I can just write a minus 2. So this, the third term is equal to the second term. And then for the fourth term, it's just scalar product of v with v, like so. So this is actually a v and not a u, so let's try and be a bit more clear in my handwriting. Apologies. Okay, like this. So now, next step is calculating the partial derivative with respect to a certain coefficient uk and then putting that equal to 0 in order to find the values of uk that minimize this energy. Now what we need to do is we need to take these partial derivatives of scalar products of the following form. So rather than writing duk here, I'm going to be a bit lazy and use the notation prime for this, which is usually reserved for total derivatives, but let's not worry about this. So just in case you're not exactly sure or confident how to calculate that, just remember that this scalar product is basically an integral of the product of f and g. And since this is all linear, if we bring then the derivative operation inside the integral, we can use our friend, the product rule. So this becomes the integral of f prime g plus fg prime, which of course is f prime g plus fg prime with scalar products. So the scalar product, if we take a derivative, just behaves like the ordinary product rule for derivatives. So just in case you were doubting about that. So let's make some room here and try and figure out what the derivative with respect to a certain value uk is of, for example, a sum like this. Just as an example, and to make things more concrete, let's take the derivative with respect to, let's say, u2. So we have, for some reason, yeah, there we go. So we have the u2 of a sum, and let's only take two terms in the sum, just as an example. So lu1 b1 of x plus lu2 b2 of x. Now, for the purposes of our partial derivative with respect to u2, the only thing that matters and the only thing that varies is u2 itself. All of the other stuff here is just constant. So taking the partial derivative with respect to u2, that first term vanishes. The only thing we're left with is lb2 of x, because this is a constant in front of a linear factor of u2. So hopefully, by looking at this simple example, we now know how to calculate all of those derivatives. So let's proceed. Let's calculate d modulus r squared duk and put that equal to 0. So for our first term, excuse me, we have a product here. So we can use the product rule to first calculate the derivative of the first factor. So the first factor is this sum here. If we generalize what we have here from the value 2 to an arbitrary value k, that just tells us that we should have lbk of x here. And then we copy the second factor, j uj bj of x. Okay. We're still not finished with the first term because we need the other contribution. So for that second contribution, we just copy the first factor, sum over I, ui bix, and then we take the derivative. That becomes lbk of x. Okay, so now we've taken the derivative of that first term here. Let's take a look at the second term. That's actually a lot easier. So that's minus 2. And the reason it's a lot easier is, of course, because this v of x doesn't really come into play here. Does not depend on u. So we have lbkx again, v of x. And the final term here, v squared, does not depend on u at all, so we don't need to worry about that. And this thing we should put equal to 0 in order to figure out how we can minimize that expression. If you look again at these first two terms, again, it's no longer a product of two series expansions, so the summation index doesn't matter. And since we have said that we're looking at a scalar product which commutes, we can flip the order here. Actually, the first term and the second term, they're just the same. So we can combine them and simply write that we have 2 times the summation over L U UI B I X LBK of X minus 2, and then we have the summation, and again let's flip the order here because our scalar product commutes, LBK of X, and this thing should be equal to 0. Again, we can get rid of the 2's here. We can factor out our LBK, which appears in both of these terms. Since we're all among linear friends here, we can just factor that one out to finally have that L summation over I ui bi x minus v of x for our first vector, L bk of x is equal to 0. So if you solve this linear system, you will find the u values that minimize the energy in our functional. But wait a minute, if you now go back to the derivation of the method of weighted residuals, you will of course immediately realize that this thing is again our residual. And what you do here is you take a scalar product with weighting functions. So what you show here in this case is that the weighting function is given by L times bk. So we've shown that for this particular choice of weighting functions, our method of weighted residuals actually boils down to minimizing the energy in the residual.